The Hydrologic Cycle. Objectives. Several processes and factors are involved in driving the global water circulation. This lesson is aimed at highlighting the world's water cycle and its major components and contributions. The objectives of this lesson are to learn about the basic concepts of the hydrologic cycle, the components of the cycle, the role of individual components, the water balance estimation concepts, the role of hydrological cycle in promoting the other environmental and biogeochemical cycles on the earth. After attending this lesson, the learner should be able to describe about the world's water circulation, elements of water cycle, and their interrelationships. Introduction. Earth contains enormous amounts of water in the form of reservoirs. Water exists in the atmosphere, lithosphere, hydrosphere, and biosphere. Among all these segments, water masses are in continuous circulation. It is, in general, called as the hydrologic cycle. It is also called as the world's great water cycle, since it is the driving wheel for all the movements of available water resources on the planet Earth. It is necessary to identify the cyclic and circulatory routes of water masses in all the spheres of the Earth. Several processes and factors are involved in driving the global water circulation. This lesson is aimed to highlight the world's water cycle with all its components and contributions. The Earth as a water planet. The planet Earth is called as the water planet. It is due to the fact that the Earth is probably the only planet in the solar system which has a huge mass of water. On the planet Earth, the primitive life got originated only from the water mass. Most of the Earth's surface is covered with water. Water exists in all the segments of the Earth. The hydrosphere is the sphere of water on Earth. It is a discontinuous layer containing both fresh water and saline water. The subject, hydrology, deals with all aspects of the hydrological cycle. The world's water. The world's water is not in static form. It is in continuous motion. It also transforms from one state to the other. The water gets temporarily stored and moved in the form of surface water in rivers, lakes, ponds, ice caps, and below the surface as groundwater. Oceans form the biggest and largest water reservoirs. All these water bodies are called as water reservoirs. The duration of stay and storage of water in every reservoir varies due to varying geological, environmental, and other conditions. This is called as the residence time of water. Water moves from one reservoir to the other. The sun's radiant energy plays a very significant role in this movement. Atmospheric pressure, wind blows, temperature, and the amount of water vapor present in the air all play a dominant role in these processes. The rates of movement of water and the quantities involved in the cyclic processes are the major aspects involved in the hydrological sciences. There is an endless circulation of water among all the spheres of the earth. It is popularly known as the hydrologic cycle. It is necessary to learn about the hydrologic cycle when we intend to analyze the water resources of the region and the world. Concept of hydrologic cycle. Water gets transformed from liquid to solid, solid to liquid, liquid to vapor, vapor to liquid, and vapor to solid states. The sun's radiation, acceleration due to gravity, ability of the water to flow, and several other properties of water make this transformation more effective and regular. The basic input to the world's water masses comes from precipitation. Precipitated rain or snow falls over land. Processes like infiltration and percolation move the water down to groundwater systems. Some amount of water flows towards the sea as runoff. The surface water collected in lakes, ponds, swamps, seas and oceans gets evaporated into the atmosphere. The vegetation transpires the water collected from the soil moisture. Evaporated and transported water enters into the atmosphere as vapor. Collected water vapor gets condensed to form the clouds. Clouds move towards the land and start precipitating again. These processes continue. This endless circulation of water is known as the hydrologic cycle. It is of two kinds as terrestrial hydrologic cycle and global hydrologic cycle. The terrestrial hydrological cycle is of a special interest as the mechanism of formation of water resources on a given area of the land, like a river basin or a watershed. The global hydrological cycle deals with its role on the global climate and other geological and physical processes. It is obvious that the role of different processes involved in the hydrological cycle and their description have to depend on the chosen spatial temporal scales. Components of the hydrologic cycle. The circulation of water masses seen in all spheres of the earth involves several causative factors and components. The major components or elements of the hydrologic cycle are precipitation, evaporation, transpiration, evapotranspiration, surface runoff, condensation, infiltration, groundwater baseflow, sublimation, interception. Global hydrologic cycle. Most of the Earth's water masses reside in the oceans. Continental water makes up about 3.5% of the Earth's water. About 3/4 of this amount, 29 million cubic kilometers, is present as polar ice caps and glaciers. About 5.3 million cubic kilometers as deep groundwater. Thus, only the remaining fraction can take part in the water exchange between the oceans, the atmosphere, and the continents. This remaining part includes shallow groundwater and soil moisture, water in lakes, reservoirs and swamps, water storage in river channels, biosphere water. The amount in the atmosphere is only 0.013 million cubic kilometers, but it plays a very crucial role in the global water cycle. Terrestrial hydrologic cycle. The key component of the terrestrial hydrological cycle is generation of river runoff and movement of water in the river networks. As stated previously, the mainland area units may be river basins and watersheds. They are ideal hydrologic units. The sizes of these areas vary from tens of square kilometers to several thousand square kilometers. Within these hydrologic units, distinct spatial differences in topography, climate, geology, structure, vegetation, soil properties, land use, land cover, and other features may occur. The terrestrial hydrological cycle considers all aspects of the main processes and factors that control the processes as well. The underlying factors. The following are the major factors involved in controlling the movement of water masses in the hydrologic cycle. Application of energy that promotes transformation from one state of matter to the other state. Inherent properties of matter, that is, water. Dimension and geo-environmental settings of the reservoirs. Gravity, which promotes flow. Air, which promotes mobility of water molecules. Earth's revolution and rotation, which are responsible for climate and weather cycles. Condensation, The sun's radiant energy evaporates water from surface water resources, including seas and oceans. This water rises upwards as water vapor and reaches the atmosphere. The process of evaporation continues until the air becomes fully saturated with maximum amount of moisture. It is called as saturation humidity. It is directly proportional to the temperature of the air. It is expressed in grams per cubic meter of air. At 0 degrees centigrade, humidity of air is 4.874 grams per cubic meter, and at 30 degrees centigrade, it is 30.38 grams per cubic meter. Relative humidity is a term used to denote the ratio of the water vapor content of the air to the water vapor capacity of the air. The term absolute humidity is used to denote the number of grams of water per cubic meter of air. If the air mass reaches the dew point, then the condensation process begins. Humidity is measured using hygrometers. Through the process of condensation, clouds are formed and moved towards the land frontiers. Condensation in the atmosphere takes place around small particles of substances present in the air which have the affinity for water. These form the hygroscopic nuclei surrounding the condensation nuclei. These condensed water vapor masses get precipitated in the form of water molecules. Precipitation is the process by which this transformation happens in the atmosphere under certain specific conditions. Condensation depends on several factors. The notable ones are adiabatic cooling, mixture of two air masses of different temperatures, contact cooling, radiational cooling. Among these, the most important condensation process is the adiabatic cooling, which leads to all kinds of precipitation. Condensation leads to cloud formation. Condensed clouds of smaller sizes may quickly disappear on a hot day. Cloud condensation nuclei, which vary in size from 10 to the power of minus 5 to 10 to the power of minus 1 millimeter, are required to condense water vapor at dew point. Typical cloud condensation nuclei are meteoric dust, wind-blown clay and silt, volcanic material, sea salt, and combustion products. Natural concentrations of cloud condensation nuclei vary from 100 to 300 cubic centimeters, but may locally become 10 to 100 times larger due to human activities. When a vapor condenses, heat is released. Condensation also leads to the formation of fog. Before precipitation to happen, the cloud droplets sized from 0.001 to 0.2 millimeters have to grow to 0.4 to 4 millimeters in diameter to reach a fall velocity that exceeds the rate of uplift. Cloud droplets may grow at temperatures above 0 degrees centigrade. The droplet collision occurs due to differences in fall and lift velocities caused by the differences in droplet size. The world's water vapor is equal to about 2.5 centimeter thickness on an average if it is distributed all over the surface of the globe. Precipitation. Precipitation is the process of transforming the water vapor into a liquid or solid form, depending upon the temperature of air near the clouds. The term precipitation is a common term. It includes a variety of forms of precipitation. It includes mist, rain, hail, sleet, and snow. The term precipitation and rainfall are always used synonymously. Precipitation mainly depends on the water vapor present in the atmosphere. When the air temperature is well below the freezing point, clouds may form tiny ice crystals. For precipitation to form, a sequence of 4 processes must occur. Atmosphere must have sufficient water vapor present, which is cooled to dew point. Condensation of water vapor on cloud condensation nuclei. Growth of water droplets and importation of water vapor. Whenever the water vapor in the air is cooled down below the temperature corresponding to the pressure of saturated vapor, condensation occurs on dust particles, globules of water, grass, or other foreign objects. Condensation of moisture out of the atmosphere above the immediate surface of the earth occurs on dust particles or suspended globules of water and takes the form of fog, cloud, rain, snow, or hail. During warm weather, cyclonic areas are usually accompanied by thunderstorms. A thunderstorm, as the name implies, is a storm accompanied by lightning and thunder, and usually precipitation. The condensation which results in the precipitation of moisture from clouds is caused by what is known as dynamic cooling, that is, the cooling resulting from the consumption of heat in the work of expansion of the rising vapor, as previously explained. These conditions are fulfilled in the atmosphere every time during the monsoons. Though there are several mechanisms active in the atmosphere which cool air, only the process of adiabatic cooling due to vertical uplift is able to produce precipitation of any significance. Three types of lifting mechanism of lifting moist air to a level where condensation of water vapor to take place are available as convective, cyclonic, and orographic. Under the convective process, the lifting occurs due to differential heating of a region where the warmer moist air rises in relation to colder surroundings. Lifting in a cyclonic process occurs due to convergence of moist air into a low pressure area. Orographic rain occurs due to mechanical lifting of moist air on mountain slopes. The rainfall. Rainfall is the most common form of precipitation occurring in almost all parts of the world. In tropical regions, precipitation is expected completely as rainfall. In the polar regions, precipitation is expected to be completely as snowfall. In mid-latitudes, at high altitudinal zones, precipitation occurs as snowfall, sleet, and ice. All these are called as forms of precipitation. 4 conditions are necessary to get sufficient amount of rainfall. They are a mechanism to produce cooling of the air, a mechanism to produce condensation, a mechanism to produce growth of cloud droplets, a mechanism to produce accumulation of moisture of sufficient intensity to generate rainfall. The amount of rainfall occurring in a place is measured using a rain gauge. A network of rain gauges is needed to analyze the rainfall of a larger region. The total rainfall on the Earth's land surfaces amounts to 110,000 cubic kilometers. It returns to the atmosphere via evaporation and evapotranspiration. The snowfall. The snowfall is another form of precipitation. It comes as a percentage of annual precipitation. It accounts for 5% globally. The snow melts and creates stream flow. On the prairies, the snow melt accounts for about 80% of the stream flow and water stored in sloughs. The snowfalls are measured using snow gauges. The snow gauges are shielded and mounted on brackets such that the gauge can be raised as the snow accumulates inside and can be measured. The most accurate method of determining snowfall amounts requires frequent measurement of changes in the depth of snow on ground because snow tends to quickly settle and undergo metamorphosis. It is measured in depth of snow. The hydrological significance of snow are: total annual snowfall is only one factor determining the contribution of snow to a water budget. Snow is first stored for days to months before participating in the hydrological cycle. Evaporation. Evaporation is the process of converting a liquid or solid into a gas through the transfer of heat energy. In hydrologic cycle, this conversion is towards water vapor. Heat energy can convert water mass or ice into a vapor. Evaporation occurs more rapidly when there is increase in temperature and also flow of wind. It also depends on the boiling point and vapor pressure. The greater a substance's vapor pressure, the more rapid the substance gets evaporated and escapes into the air. Open water evaporation is the theoretical evaporation flux from a smooth, shallow water surface with no storage of energy when subjected to the ambient meteorological conditions. Pan evaporation is the evaporation flux from an evaporation pan. Soil evaporation is the evaporation flux from the soil. Under the conditions of constant temperature, humidity and wind, evaporation from the large water surfaces of the earth must remain constant. A temporary increase in temperature results in increased evaporation and also increased precipitation. Water gets evaporated more rapidly in dry air. This is due to the fact that dry air has only a fraction of the maximum vapor pressure of water. It is also essential to note that the evaporating molecules absorb heat from the surroundings. Huge volume of water evaporates from the ocean surfaces. The amount varies from place to place. It is called as evaporation discharge. The greatest amount is around the equator, where the intensity of solar radiation is more. The factors affecting evaporation are air temperature, relative humidity, incoming radiation, wind speed, duration of bright sunshine, geomorphic conditions of the region. The amount of water getting evaporated from a free water surface is measured using evaporimeters or pans. Evaporation from soil surface. The water molecules present in the soil matrix also get evaporated with great difficulty, unlike those which are released from the free water surfaces. The amount of water vapor present in the atmosphere varies greatly from time to time, but the dry gases do not change materially in quantity from season to season. It may be remarked at this point, however, that about half of the total moisture present in the atmosphere is found below an elevation of about 6,000 feet, and less than 1/10 of it occurs above an elevation of 20,000 feet. Transpiration. Transpiration is the process of releasing the water absorbed by the plants through their root system after utilizing the nutrients for building their tissues in a specified time. Vegetation, including numerous growing plants, play a significant role in the hydrologic cycle. The water which is drawn into the plant rootlets from the soil moisture, owing to osmotic pressure, moves up through the plant stems and leaves. Through the stomatal openings, the water is released out as water vapor. The amount of transpiration depends on the density and size of the vegetation existing in place. The amount of water used for irrigating the crops get transpired into the air. Transpiration is dominant during the growing season of crops in agricultural lands. Most of this happens during daytime when photosynthesis is active in plants. Transpiration is limited due to the shortage of soil moisture in some places. The controlling factors of transpiration are temperature, solar radiation, wind, and soil moisture. Evapotranspiration. Evaporation is the evaporation flux from intercepted water and from the soil. Transpiration is molecular diffusion of water vapor through the stomatal aperture of leaves. Evapotranspiration is the combined effect of both evaporation of water from the soil, surface water bodies, snow, ice, and transpiration from vegetation. In a well-irrigated land, it is difficult to separate evaporation from transpiration. The total water loss due to both evaporation and transpiration is called as evapotranspiration. Majority of the water loss due to evapotranspiration happens during summer months and growing seasons. There will be no or little loss expected during winter months or period. Two terms as potential evapotranspiration and actual evapotranspiration are used to denote these conditions. Actual evapotranspiration is the total evaporation flux of a cropped surface. The actual evapotranspiration depends mainly on atmospheric factors, soil water characteristics, and physiological factors of the crops and other vegetation. The rate of evapotranspiration is controlled by several climatic, hydrologic, soil, and geomorphological conditions of a region. Soil texture and permeability play the major roles in this process. Potential soil evapotranspiration is the theoretical evaporation flux from the soil if the soil would sufficiently be supplied with water. Potential evapotranspiration is the sum of the potential soil evaporation and transpiration. The major use of potential evapotranspiration data is generally for water resources planning, agricultural and irrigation management, and research. Surface runoff. Runoff is the quantity of water that is discharged or runs off from a drainage basin during a given time period. Runoff data may be presented as volumes in acre feet, as mean discharges per unit of drainage area in cubic feet per second per square mile, or as depths of water on the drainage basin in inches. It is measured by establishing stream gauges at selected places of the river courses. The term runoff refers to the overland flow of water after every rainfall or snow melt. The overland flow starts when the rate of rainfall is greater than the rate of infiltration of the soil and increase in the amount of slope. Initially, runoff starts as small streams and the water gets added from many such streams. Finally, all of these reach and confluence with a lake or stream or directly with seas. The volume of water leaving through a river is known as river discharge. It is considered as precipitation returning to the sea. Stream flow is the discharge that occurs in a natural channel. Although the term discharge can be applied to the flow of a canal, the word stream flow uniquely describes the discharge in a surface stream course. The term stream flow is more general than runoff, as stream flow may be applied to discharge whether or not it is affected by diversion or regulation. Factors controlling runoff. The flow of any stream is determined by two major groups of factors. The first set belongs to the geomorphological factors of the drainage basin. The second set of factors depend on the climatological variables. The climatological factors are rainfall, intensity and type, duration of rainfall, distribution of rainfall, direction of storm movement, soil moisture conditions. The geomorphological factors include land use, land cover, type of soil, area, shape, elevation, slope, network of drainages, and indirect influences for runoff. Infiltration. Infiltration is the downward percolation of rainwater or snowmelt water into the soil horizons. The downward movement of water happens in the topsoil layer, especially through the smaller pore spaces present in the soils. Infiltration is governed by two forces, as gravity and capillary action. The smaller pores offer greater resistance to gravity. Very small pores pull water through capillary action in addition to and even against the force of gravity. Tensiometer is used for the measurements of soil water properties. After every rain, the zone of soil moisture obtains the first part of the rainfall. The rate of percolation is known as infiltration rate. It is measured using infiltrometers or lysimeters. Infiltration rates are measured by conducting infiltration tests. The rate of infiltration varies from soil to soil. It depends on the hydrologic properties of soils like porosity and permeability. The process is also known as percolation. The percolating rainwater ultimately reaches the groundwater zone. The process of infiltration happens only when there is space available for addition of water within the soil surface. This depends on the porosity of the soil and the rate at which previously infiltrated water can move away from the surface through the soil. The maximum rate that water can enter into a soil layer in a given subsurface condition is known as the infiltration capacity. Infiltration rate in soil science is a measure of the rate at which a particular soil is able to absorb rainfall or irrigation. It is measured in inches per hour or millimeters per hour. The rate decreases as the soil becomes saturated. If the precipitation rate exceeds the infiltration rate, runoff will usually occur unless there is some physical barrier. The factors that affect infiltration are porosity and permeability of the soils, structure and texture of the soils, surface entry possibilities of the soils, transmission through the soil, already available soil moisture and its depletion, characteristics of the fluid. All terrestrial plants and forest vegetation thrive due to the presence of infiltrated water in the soil horizon. The maximum rate at which a soil is capable of absorbing water is called as its infiltration capacity. Percolation is favored by a slow and steady precipitation, permeable soil, and a flat or very gentle slope. Steep slope may leave the water over the surface. Interception. Interception is the process of retaining water on the leaves of vegetation. A small amount of rainfall is intercepted by vegetation. The rainfall which is not intercepted is known as throughfall. The water which reaches the ground via stems and leaves is called as stem flow. These are the three main components of interception. When rain falls onto a forest land, a proportion of it is intercepted by the canopy and evaporates back into the atmosphere. This water is not playing any role in the terrestrial portion of the hydrologic cycle. This is called as canopy interception loss. Interception can amount up to 15 to 50% of precipitation, which is a significant part of the water balance. Although interception storage is generally small, the number of times that the storage is filled and depleted can be so large that the interception flux is generally of the same order of magnitude as the transpiration flux, flow accounted as loss. Snowfall is also intercepted by trees, especially the coniferous trees can store much snow for interception. The storage capacities of vegetation, while intercepting rainfall, vary with the type and structure of vegetation and also with the meteorological factors. The experiments have shown that about 8 millimeters of rainfall can be intercepted by the vegetative zones. This water is evaporated back to the atmosphere. The rate at which it goes back to the atmosphere is known as interception rate. The controls on interception rate are vegetation characteristics, growth form, trees, shrubs and grasses, plant density, plant structure, number, size, flexibility, strength and pattern of branches, texture, surface area and orientation of leaves, plant community structure. Meteorological factors, precipitation intensity, precipitation duration, wind speed, type of rainfall, rain versus snow, precipitation frequency. Groundwater baseflow. The rainwater that is falling over the ground surface percolates down through the soil and reaches the groundwater zone. Depending upon the slope of the groundwater system, the groundwater moves towards the rivers, lakes, or the oceans. This flow of groundwater is known as baseflow. It depends on the hydrologic properties of rocks forming the groundwater systems. This is an invisible flow of water. A river may become a losing stream or a gaining stream depending upon the contribution of stream water down the earth or groundwater into the stream, respectively. The subject of groundwater hydrology deals with all aspects of groundwater. Computation of groundwater balance is made to utilize the available groundwater resources when there is no surface water facility available in a region. Sublimation. Snow-covered zones also experience losses of water through direct evaporation. The process of direct evaporation of snow into water vapor is known as sublimation. The solid does not pass through a liquid state for evaporation. It is very difficult to distinguish between evaporation and sublimation from snow. Air temperature plays a significant role in addition to wind in sublimation to happen. Global water balance. The direct input sources of water for the lands and seas are from precipitation. The major output sources are from evaporation, transpiration, sublimation, interception, and evapotranspiration. There is a balance of water existing as storage in the form of groundwater, surface water bodies as lakes and streams, ice caps and glaciers, and as seas and oceans. These components can be analyzed using a simple mass balance equation called as water balance equation. This equation considers the inflow, outflow, and changes in storage reservoirs of fresh and salt water. The basis of the equation is inflow equals outflow plus or minus changes in storage. This equation can be expanded as P minus E minus T minus RO equals delta S, where P equals precipitation, E equals evaporation, T equals transpiration, RO equals runoff, delta S equals changes in storage. This equation balances the availability of water for a specific period of time in any region of the world. Computation of a hydrological budget is needed for all practical purposes of water resources consumption and management. Earth's other cyclic process. The hydrologic cycle is the primary cycle of the planet Earth. It becomes the focal concept and driving mechanism for part of the rock cycle, geochemical cycle, and the sedimentary cycles of biogeochemical cycle. In the rock cycle, weathering, mass wasting, erosion, transportation, and depositional aspects of sediments are carried out by the components of hydrologic cycle. The sulfur and phosphorus cycles of biogeochemical cycles are driven by the components of hydrologic cycle. All trace elements and their motilities among rock, soil, water, plant, and animal are all controlled by the hydrologic cycle. River basin as a hydrologic unit. Drainage basin is a part of the Earth's surface that contains a drainage system with a common outlet for its surface runoff. Hydrologic unit is a geographic area representing part or all of a surface drainage basin. Drainage area of a stream at a specific location is that area upstream from the location, measured in a horizontal plane, that has a common outlet at the site for its surface runoff from precipitation that normally drains by gravity into a stream. Drainage areas given herein include all closed basins or non-contributing areas within the area unless otherwise specified. The The total volume of water on the earth in its liquid, solid, and vapor forms has been the same since the formation of the planet. Rivers are natural water courses. River water flows over the land surface in small channels after draining discrete areas. The existence, size, and flow of a river water are influenced mainly by the availability of surface water, a river channel in the ground, and an inclined surface. A river basin refers to the fall catchment zone of a river and its tributaries with a clear-cut water divide separating it from other basins. All network of streams belonging to the main river and its tributaries are enclosed well within the river basin. The boundary of the basin is denoted as basin boundary. There will be a single outlet for any drainage basin. The main river may confluence with a reservoir, a lake, or an ocean. The stream of a large river basin may have a very wide delta at the point of confluence. The catchment zone of tributaries and their streams are referred to as subbasins. The small network of streams joining the tributaries may have their own mini catchment zones. These are called as watersheds. A watershed covers area above and below the earth's surface. The small channels and streams drain water towards a surface water body like a pond or a river. Bigger watersheds may contain numerous tributaries and their corresponding catchment areas. The watersheds are considered to be the smallest hydrological units of a large river basin. The contributions of all watersheds are cumulatively considered for the yield or outflow of the river basin. A quantitative estimation of water balance of each watershed is possible as the parameters are measurable, suitable, and ideal for computations. Hydrologic cycle and natural hazards. Floods are the major natural hazards arising out of the surface runoff of large basins and their rivers. Floods cause severe damage to life and properties. They also damage the grown-up crops and rural and urban settlements. It is a part of the hydrologic processes that are happening in a short span of time after a heavy rainfall along the river courses. Floodplains are the zones severely affected due to this hazard. Thunderstorms are yet another hazard coming due to hydrologic processes in the atmosphere. These are issues requiring proper disaster management methods. Sudden and heavy downpour of precipitation can cause severe damage to the population. Drought is a major issue arising out of continuous failure of monsoons in any area or a river basin. Landslides are hazards occurring after heavy rainfall in hilly regions. Hailstorms and snowfalls create a lot of problems in the mountainous and polar regions for transport, cultivation, and other activities. Cyclones are depressions created in bays and oceans due to atmospheric pressure belts. They move towards the condensed water masses. Both wind and storms create damage to the coastal belts. Proper disaster management plans are necessary to mitigate the effect of these water-related natural hazards. Units and measurements. While discussing about the components of hydrologic cycle, it is necessary to know about the technical terms which are used. The terms stream flow, runoff, discharge, and yield of drainage basin are almost used synonymously. Runoff here refers to the surface runoff. Groundwater flow is referred to as baseflow. The term groundwater discharge refers to baseflow and pumping of water from the groundwater system. The units in which all these quantities are expressed are always in relation to volume per unit of time. Volume units. Gallon is also the standard unit of measuring liquids. It is used to express the storage and flow capacity in cubic feet or cubic meter. It is a unit for expressing volume. Acre feet is yet another unit. It refers to the quantity of water required to cover 1 acre to a depth of 1 foot. It is a unit of volume for expressing the storage in reservoirs also. The forms are inches or centimeter per area depth per unit area. Rainfall and evapotranspiration are expressed as centimeter depth on drainage area. Acre feet per day refers to the rate of flow of a stream. Volume of water flow is normally expressed in cubic meters per second or cubic kilometers per second or in million gallons per day or million meter cube. Appropriate conversion factors are available for converting these components from one unit to the other. In all the old textbooks, FPS, feet pound second system, might have been used by the authors. Now, the SI units, Systems International, are invariably used by all.